using A36 steel. And the diameter of our column is going to be 50 millimeters. Again, we want the maximum intensity with a factor of safety of 2 against buckling for that column BC. For this material, the A36 steel, again, we're going to need these values just like we did before. Young's modulus is 200 gigapascals. We're back into metric here. And the yield limit, the yield stress is 250 megapascals. So first thing we need, if we're looking at buckling, is we need to know what is the normal force in the column, because that's what's going to cause it to buckle. So what we can do here is we can turn this into a kind of a combined frames and machines and internal problem. Again, I am interested in what's the internal force in that column. So I can remove it from the pin at A, and I can make a cut through the column to see what the load in the column is, since that's what's going to cause it to buckle. And we know it's a two-force member because it's pinned at B and it's pinned at C. So we know it will only carry an internal load. Some intensity W, and it's going over 6 meters. By some moments around point A. I don't really care in this problem what the pin reaction is, but summing moments around point A, I'll have 6 times W is the force of my distributed load, times 3, plus 6 times P. So I know that the force in the column is going to be 3 times W, which ultimately I need to find. I know it's in compression, because assuming W has to be positive here, then P is going to be negative. I assume tension, as I always do, so it's going to be in compression. So I do have to worry about buckling as well as worrying about crushing. So I do want to consider both. So if I look at this connector from B to C, it's going to be 3 meters tall. And in this case, it does have a symmetric cross-section because it's circular. And in this case, I have a pin that goes into the, from how I originally said XYZ, the pin is going along the Z axis here. So it's going to be pinned around Z, and it's going to be fixed about the X axis. So it is free to rotate around Z, but it's locked in at X. In this case, I'll simplify it because it is symmetric. Really, that shorter effective length means it's definitely not going to buckle around the x-axis, although we'll do those calculations just to show that. If it's going to buckle, it's going to buckle around Z, since the pin connection makes it easier to buckle. So I do, in general, still need to consider it could buckle around X, it could buckle around Z. In this case, IXX and IZZ are the same. I can make that calculation. The area moment of inertia of a circular cross-section is going to be pi over 4 r to the 4th. So 25 millimeters to the 4th power. The moment of inertia about both axes, I get 3.07 times 10 to the negative 7 meters to the 4th power. So for the sake of completeness, I'll look at buckling around the x-axis, and then what does it take to buckle around the z-axis. So for P critical, I'll have pi squared times the Young's modulus times the moment of inertia about the x-axis, which is also that about the z, 3.07 times 10 to the negative 7. And now I have to look at what's the effective length when I'm going around the x-axis. Again, it's pinned around the z. It's able to make that... it's able to rotate around the z-axis. That's what makes it a pin. But around the x-axis, that pin prevents it from rotating around the x-axis. So with respect to the x-axis, it's going to be a fixed connection, meaning that k value, like we saw in the last one, was 0.5. times the actual nominal length of 3 meters, quantity squared. For it to buckle around the x-axis, it would take 269 kilonewtons of compressive force. Again, it can also buckle around the z-axis. We want to check that as well. So P critical z, the numerator is actually unchanged for this one because I is symmetric. But our k value changes around the z-axis because about z, it's pin-pin connection, which means that the effective length, or the coefficient, is just 1. So our denominator is now 4 times the size. So about z, it will then take 4 times less, or a fourth as much, to buckle around z as it does about x. It takes only 67.3 kilonewtons to buckle it around the z-axis. So we've determined that if it were to buckle, it would buckle around the z-axis first because that's the direction it's pinned and it's symmetric. But we haven't yet established that it will buckle before it crushes. So like in the last one, we wanted to compare what would the stress be when it's about to buckle and compare that to the yield stress in our material. So 67.3 thousand newtons over the cross-sectional area of pi times 25 times 10 to the negative third squared. So the critical stress, or the stress when it's just on the verge of buckling, we get 8.57 megapascals. And if we compare that to the yield stress of A36 steel, we're well below it. We're well below the 250 megapascals. So indeed, this is going to buckle much, much sooner than it would crush. It would take a lot more compressive force for it to go beyond the yield limit. It'll buckle well before that. So when this fails, it's going to fail due to buckling around the z-axis. So we're not quite done yet because what we were searching for was not what is the critical force to buckle it. We were searching for what's the intensity we can apply before it buckles, including a factor of safety of 2, guarding against buckling. So at this point, I can apply my factor of safety because I now know what causes it to fail. It's this critical load being too high causes it to buckle around Z. So at this point, I apply my factor of safety, is when it actually fails over what I'm going to design it to handle. It actually will fail at 67.3. So I will design it so that the force in the column is only at maximum 33.6. So the last step is I can now relate the internal load, or the load in the column, to the intensity I have. So this is where I want to be. This is also in compression. I want to be careful of the sign here. W has to be positive. P is really negative based on this definition. So really here too, when I put it back into here, the value of P, I really should use a negative because it's a compressive load. So W is going to be P design over 3. So the maximum my intensity can be, I take my design load, divide by 3. I can have at highest 11.2 kilonewtons per meter.